Well, hello students. Today we are going to do some chemistry. I am doing what people have asked me to do, which is something on paper 3. Paper 3 is the practical, and we are going to look at some of that. I have sent today two small pieces of information via Challenge Aid to your teachers and to you. One is a lesson which I did 18 months ago from a laboratory where I went through some of the practical details, and one where somebody is going through the 2022 paper 3. And they're both useful, they're both worth watching. I think they are both worth doing. Okay. I think they're both worth watching. But today I'm going to do paper 3. Now, paper 3, how many of you have done quite a lot of practicals, some practicals, or very few practicals? So if you've done many practicals, show me like this, please. St. Mary's, Kabiro, show me lots. You've done lots of practicals, students. Not too many practicals, not many, very few practicals. Okay, so some people like this, some people like this. Okay. Two big things in paper 3. Kabiro. Thank you. Two big things in paper 3. Number one, read as much of the paper quickly. When you get in there, read it, flick through very quickly, so you know how much you have to do. If you do this, then you will know in your 2.5 hours how many practicals you have to do. Some people go too slowly, some people go too quickly. You have to get it about right. That's number one. Number two, when you write things down in the paper, you have to be really clear about your observations and your inferences. Observations are color changes, bubbles, that sort of thing. You cannot see carbon dioxide. You can see bubbles of a gas. You can see effervescence. You can see even a gas is given off, but you cannot see carbon dioxide, hydrogen, that sort of thing. You can see bromine water going from orange, yellow to colorless. You cannot see it. You shouldn't just say it is decolorized, because they want to know what color it was before and after. If you are using potassium dichromate, you should say the orange potassium dichromate or the potassium dichromate changes from orange to green, if it does. Or if it doesn't change color, don't just say it doesn't change color. Say it remains orange or yellow, whatever color it is to start with. If the indicator is methyl orange, you can't say it just goes red. You should say it goes red from yellow, or it starts yellow and turns red, or whatever. Always tell them what it was before, what happened during, what it was like afterwards. In your observations, colors, bubbles, precipitates, colors of precipitates in observations. Inferences can be carbon dioxide is given off, because if you know that you have added an acid, let's say, and it bubbles a lot, effervesces, and you do a test, it extinguishes a glowing lit splint, then you can say in the inference, this is carbon dioxide from a carbonate, okay, or a hydrogen carbonate, a bicarbonate. Okay, it's very important that you don't mix them up. Observations, what you see, sometimes what you smell. If you made an ester, you would smell a nice smell, a pleasant smell, a sweet smell. But most of the time, it will be what you see. Inferences, infer is what I know to be true because I have seen what I have seen. Okay, so what we're going to do today is we are going to look at the 5 main types of practical which they ask you to do in paper 3. I'm going to do it by sharing a screen. I'm going to write stuff. I'm not going to write stuff on the board behind me because last time it was difficult to see. So I'm going to use a small screen, which is very difficult to write on. So you will have to forgive my handwriting, but we will not worry about it too much. So hopefully you will be able to see. So here is these are the 5 types of practical which we get. The first one is a simple experiment like collecting a gas. This might be to look at rate of reaction. It might be to work something out. I'll show you an example of something which is about working out. The second one is titrations using burettes, pipettes, which may include making up solutions. And for that, you have to know the color changes of indicators. The third one is enthalpy or energy heat change measurements using a thermometer, measuring before and after, perhaps drawing a graph and working out what the temperature change is, and then using MC delta T, which you probably know, mass, specific heat capacity of water, and the change in temperature to work out enthalpy. Then we have, for number 4, we have organic identification. That will include, sometimes they will ask you to burn a small amount of it, or they might ask you to measure its pH, or they might use indicators on it, or they might try to oxidize it using potassium dichromate, and so on. And then we have inorganic identification. We have cations and anions, cations being positive, metals, hydrogen or ammonium, and anions. And the cation tests are normally just using sodium hydroxide or ammonium hydroxide. And the anion tests are using things like barium nitrate or chloride, silver nitrate, acid to test for a carbonate, and so on. Okay, so those are the 5 types of practical, and I'm going to try and look at all 5 of them today briefly. So in the first one, we might have a setup like one of these 2 beneath. Okay, so either you might have a conical flask, like on the left, you might have the conical flask or a boiling tube, and you've got 2 chemicals reacting here and the gas going up through what we call the delivery tube into a gas syringe. These are very precise. It's very easy to read and it's quite easy to use. In the second one, same idea, but this time we are collecting a gas over water because the gas is not very soluble. So a gas like hydrogen really doesn't dissolve in water at all. Carbon dioxide dissolves just a little bit. Some gases could not be done in this way. So if you had sulfur 6 oxide, that sulfur 6 oxide, SO3, would dissolve completely. The bubbles would start going up and disappear as they go up through the water. It's quite strange to watch. So one of these 2 are quite likely, and there are some problems. If you are doing one of these practicals, they will normally ask you to measure the gas produced. But there is the problem that the gas can escape when you are adding the chemicals together. So they tell you to weigh out, let's say, they tell you to measure out 25 cubic centimeters of hydrochloric acid, let's say, and put it in here, and then weigh out 2.3 grams of a carbonate, let's say, and put it in and connect it and collect the gas. Now, the difficulty is that as you try to put the top in, some of the gas is escaping. So you have to be ready to put the bung in really fast. Okay, really, really important that you do it really fast. If they ask you to time it and to measure the gas every 20 seconds or every 30 seconds, then that is even more difficult, and you have to get ready for it. If you get it wrong, if it starts to come out and you don't get the bung in or something, you have to say, can I start again, please? Okay, really important that you start again, because if you do not get the right volume, you cannot do the calculation. So let's look at a calculation. What I'm going to do is I'm going to go through one that I've written out here. I'm going to show you it now. Okay. So let's say we are asked to collect the gas and plot a graph. The graph we would plot would be time in something like seconds along the bottom, and the volume, let's say it's carbon dioxide, which would probably be in cubic centimeters up the side. So we'd draw the axes like this. It's very important, if you're drawing the axes, if they have not written what the axes are, that you write what they are and the units. That's really, really important that you do that. You need the units, seconds, cubic centimeters, okay? Now, you might be collecting it and measuring the volume along time, or you might be just measuring the maximum. If you plot it and it goes up, it's likely to be a graph like this, because it starts very fast, because there are many reactant particles, and as time goes on, the reactant particles, they don't slow down, but they start to run out, they start the product, and eventually you come to a horizontal bit where no more gas is produced. If no more gas is produced, one of the reactants has run out. Now, sometimes they ask you which one has run out, but normally they will tell you. Okay, so what we measure is up the side, and what is set is along the bottom. So if they say the volume of carbon dioxide against time, time goes along the bottom. Here is the maximum amount of gas. Okay, so the maximum amount of gas is here, obviously. They sometimes might ask you to measure the gas at 20 seconds or something, in which case all you do is you go from here up to the line and then across. Really simple. Let's say in this experiment that the total amount of gas is, let's say, 72 cubic centimeters. Let's say that they tell you that you're going to try and find what M is, and M is a carbonate, is a group 2 carbonate. Okay? And they tell you that you are reacting it with hydrochloric acid. Here is the equation. MCO3, 2HCl makes MCl2, and water and carbon dioxide. So let's say that you've got the carbon dioxide, this is the volume of it, so you read it off the graph, and let's say it is 72 cubic centimeters, okay? You hope it's not more than the volume available. Now, what they do then is they say, okay, what is the number of moles of the carbon dioxide? Now, you have to try to remember, if you were in the moles lessons, which I did, I showed you how to remember or how to work out the moles of a gas. And it is the number of cubic centimeters over 24,000 cubic centimeters if it is room temperature, or 22,400 if it is at zero. Let's say it is at room temperature. So the number of moles of carbon dioxide are 72 over 24,000. That will give me the number of moles of it. I put it in my calculator. It tells me that it is 0, excuse me, 0.003 moles. Now I look at the equation, and I can see from the equation that 1 MCO3 produces 1 CO2. So 1 mole of MCO3 will give 1 mole of CO2. So if I have made 0.003 moles of CO2, then I must have started with the same number of moles of MCO3. So that is equivalent to 0.003, 003 moles of MCO3. Now, let us say that in the practical, they asked me to weigh out 0.3 grams. Okay, so at the beginning, they told me to take a certain amount of hydrochloric acid and 0.3 grams of MCO3, and I reacted it together. I found that the volume of CO2 was 72. I've worked out the moles of CO2. I know that because it's 1 to 1, that the moles of MCO3 is 0.003, and I know that that is 0.3 grams. Now, because moles is equal to grams, the mass, over the RFM, if I want the RFM, then the RFM is the grams over the moles, which will be 0.3 over 0.003 moles. Now that equals 100. So I've taken the grams and I've put it over the moles, and it tells me that the RFM is 100. Now, if it was MCO3 and the RFM of MCO3 is 100, then I can be sure, because the CO3, 2 minus, will weigh 60, therefore M is 40. And that means it's probably calcium. Let's just go back to the beginning. So here we go. We plot the graph. Simple. Time along the bottom, carbon dioxide volume up the side, and we just write it. We draw the graph. It starts off quickly and it flattens out. The maximum volume is, in this case, 72. They have asked me to find out about MCO3. MCO3 reacts with hydrochloric acid like this. You would be told this. I have just found that there are 72 cubic centimeters of the gas, so I work out the moles of that. 72 divided by 24,000 tells me the moles of CO2. From the equation, 1 MCO3 gives 1 CO2, and therefore I know that there were 0.003 moles of MCO3. I don't know what M is, but let's say I was asked to weigh out 0.3 grams, then those 0.003 moles of MCO3 is 0.3 grams. So if I want the RFM, that's grams over moles, which is 0.3 grams over the moles, and that gives me the RFM. Because the CO3, 3 16s and a 12 is 60, 100 minus 60 tells me M weighs 40, and that tells me it's calcium. So that's the first type of experiment. So I'm going to stop sharing just for a minute. Does anybody have any questions about that type of practical? Anybody got any questions about that? When you are doing it, the difficult thing is to get the top in, add the solid, get the top in to capture all of the gas. If you do not catch all the gas, you won't get the 72, you might get, let's say, 65, and then your calculation will be wrong on the way through. That doesn't matter. You can explain, I missed a bit of the gas, or if they sometimes ask, what errors are there? And you can say, oh, well, I was a bit slow, so I missed a bit of the gas. Okay. Any questions about that? No? Okay. Let's go back to this. The second type of practical. This is a titration. There is no point in drawing all this. If I were you, I would just draw the top, the end one here. Okay, just one to remind you. This is called a burette. The thing which we add the liquid from is a pipette. There are two different kinds of pipette. This is called a volumetric pipette because it has markings on it. This is just a teat pipette. So in a titration, there are quite a lot of things to watch for. There are quite a lot of things to do. Firstly, you need to know about the indicator. So you need to know about what sort of indicators you're using. So, oh, hello, what's happening here? Let me just. So we need to know about what the indicator is and what it does. So let's say that my indicator here is something like methyl orange. You have to know what the colors are in acid and alkali. So methyl orange is very, very popular. And in acid, methyl orange is like a pink-red color. And in alkali, it is a yellow color. And you need to know that. Okay, you need to know what those colors are so you know what the color change is. The second thing is you have to know how to fill up a burette. And it is very important that you fill this part of the burette. This here has air in it to start with. So when you fill it with whatever you fill it with, you have to open the tap to start with to fill this up with the liquid. Okay, make sure that the liquid is completely in here. That's really, really important. They sometimes ask you to make a volumetric flask. I will draw this very badly now. It doesn't matter. Ooh, look at this. It's terrible. Terrible volumetric flask. Okay. Here's a volumetric flask. In a volumetric flask, when you make up a volumetric flask, you have to put the solid in. So I put my bit of solid in. Okay. I weigh out my solid. Then I put a certain amount of liquid in. And then I shake it a lot, really a lot, to dissolve the solid. Then I fill the liquid up to the line here. And it's very important I then shake it very, very well. So I have to shake very well. If I do not, it will not be mixed. It is very, very important that it is totally, totally mixed. If you don't do that, you will not get the right results. Okay, that is really important that you realize that. They will normally then give you a table to fill out. And the table will look something like this. It will normally have like the volume at the end, the volume at the start, and the titration volume. Okay, and they will give you a certain number of goes which you can do, like this. So you put the volume at the start. Let's say I start with 0.00 cubic centimeters in, and let's say it takes 18.5 here. This is titration 1 and 2 and 3 and so on. Then down here, I write 18.5 cubic centimeters. Okay. Now, let's say that you get 18.5, 18.4, 16.9, and 18.6, okay, in 4 runs. If you get one which is obviously wrong, you ignore it. Okay, that's very, very important. You need the titrations to be very, very similar. So if you get, let's say you only do it 3 times, so we don't even do this one. If that one comes up, this one is completely wrong. You must ignore it. Okay, this is anomalous. You must leave it out. You must not include it in the average. Okay, it's really important that you do that. So just make sure that they are very, very similar. Okay, so this is what you're likely to get. The volume at the end, volume at the start, the titration volume. And you would then average those. I'm just going to get rid of this so I've got room to carry on. Just remember, any which are really bad, you just ignore them, okay? Just ignore them. There is something wrong with them. Okay. So let's say that we have an example. Let's say that they tell you that you have an unknown acid, H2X, and you are going to react it with some sodium hydroxide. And the sodium hydroxide makes Na2X and water. They will probably balance this for you, but in case they don't, you need to be able to do this. Let us say that they say you take, let's say, 6.4 grams of this in 1 cubic decimeter. Okay. And then you take out 25 cubic centimeters at a time. Okay. So 6.4. I'll just move that out of the way. Hang on. Let's just move it out of the way up here. So 6.4 grams per cubic decimeter. Okay, so you make that up in one of these, okay, in one of the volumetric flasks. Okay, so let's say we do our reaction, and let's say that we are starting with 25 cubic centimeters of this. That would go into the conical flask, so that would be in there. And let's say in our reactions we had 17.5 cubic centimeters, and the concentration of the sodium hydroxide is let's say 0.25 moles per cubic decimeter. Okay, moles per liter, same thing. It doesn't matter whether you write that like that or moles dm to the -3, it means the same thing. Okay, so here's the amount of the sodium hydroxide. Here's the amount that we've taken of that solution of H2X. Okay, and they asked me what H2X is. Okay, so let's move on. So I'm going to write the equation again. So H2X plus 2NaOH goes to, I'm not bothered about the products. I've got 17.5 cubic centimeters of 0.25 mole per cubic decimeter of this and 25 cubic centimeters of this. So I've got enough here to work out the moles of this. So I go, okay, moles for a solution is the concentration times the volume over 1,000. It's over 1,000 to turn it into cubic decimeters. So the moles equals 0.25 times 17.5 over 1,000. Now that equals, I'll get my calculator, 0.00437 moles. Now I look at my equation again, and I find that my H2X reacts with 2 sodium hydroxide, right? One of these with 2 of those. Now that means that therefore the moles over here will be divided by 2. Because one reacts with 2, so half as many moles of the H2X. So half as many moles will be 0.002185, I think. Okay, so that is 0.002185 moles in 25 cubic centimeters. In 25 cubic centimeters. Now, because concentration is moles over volume over 1,000, therefore the concentration is the moles. Well, my moles is 0.002185 over 25 over 1,000. So I could put the 1,000 up here, it doesn't matter. Okay, so that would give me 0.0874 moles per cubic decimeter. So that is the concentration of H2X. Okay, that's the concentration of H2X. So let's just make sure we've got this all right. So I've got the volume of H2X, which I measured out, right? Sorry, start higher up. So I was asked to take, let me just highlight this. Okay, so I was asked to take 6.4 grams and put it in here. Okay, so I put it into here. So this is the 6.4 grams in here. Okay, then that is this here. That's this here. And I took out 25 cubic centimeters. Then I've got my sodium hydroxide. My sodium hydroxide, I'll change the color for the sodium hydroxide. Let's make it blue. So my sodium hydroxide, whoops, my sodium, come on. My sodium hydroxide is blue. And I took 17.5 of 0.25 moles per cubic decimeter. And that allowed me to work out this number of moles. Okay. Now, from that number of moles, I could work out the number of moles of the H2X. So the number of moles of H2X is this. That's in the 25. Okay, in the 25. Now, then I can work out the concentration of the H2X, and it comes out as this. That's the concentration. Now, back up at the top, we were told that we started with 6.4 grams. 6.4 grams. Okay, so I know that I've got 6.4 grams per cubic decimeter. Now that's quite important because that means that I can work something out. Because if I want the RFM, the RFM is the grams per cubic decimeter over the moles per cubic decimeter, which is 6.4 over 0.0874. Let me just get my calculator. My calculator. Come on, calculator, wake up. My calculator says 6.4 divided by 0.0874 is 73. So that equals 73. Now, 73 is the RFM, okay? That's the grams per mole. It's H2X equals 73. Therefore, X has a mass of 71. Now, I made this up just now, so it doesn't matter what X is, but this would allow you to find out what X is. Okay? Okay. So let's just go back up. Whoops, not that far. Here it is. Here's the whole thing, okay? So we start out with, whoops, hang on, sorry. Oh, come on. We start out having to know what the indicator is like. We said we started with methyl orange, which in acid is pink, and in alkali is yellow. And you need to know that. And they often will ask you to fill in a table for that first, okay? Sorry about my handwriting, but it's a difficult thing to write on. Okay, so that's the first thing. Now, let's say that you are given the burette and asked to fill it up. You need to fill up the bottom of the tap first. That's very important. And sometimes you will be given a volumetric flask to fill up too. In this case, we are asked to fill it up. We put the solid in, we add some water, we shake it, we fill it up, and we have to shake it very, very well afterwards so that it is all completely mixed. In this example I was taking, I was saying, let's start with H2X. And you're given the equation, it reacts with 2 sodium hydroxides like that. All the rest of the calculation that we've just been doing is about trying to find out what X is. And the most important bit of it is this bit here, which I've made a bit messy, but nevertheless is this, okay? And that's starting with the sodium hydroxide here, starting with the sodium hydroxide and starting with its volume and concentration, we can work out its moles. That's the first thing. Then we work out the moles of the other chemical. This is worth 1 mark and this is worth another mark. Okay, that's really important that you realize that there are quite a lot of marks for not really doing very much at all. Okay, it's not very difficult to do that. The next bit is more difficult, but basically we were finding the concentration of H2X, and because we knew what mass we had started with, we can work out the RFM. Okay, that's quite difficult, but it's something which you should be able to do. The most important thing to remember is that if you get a wrong answer, you ignore it. Whoops. Okay, let's go up. The third type of reaction that you may be asked to do involves something like this. This is working out the amount of energy which is given out by something. I just want to talk through some of the chemical, what you've got to do in terms of the chemical technique first, okay? So let's say we've got this sort of piece of equipment. Whoops. Let's say we've got this sort of piece of equipment, and we're going to go through a particular practical. Let me just rub out that bit, sorry. Right. So you will normally be asked to measure out, let's say, 25 cubic centimeters, in this case of copper sulfate solution, okay? And let's say you are going to add some zinc to it, okay? You're going to add the zinc into there. The way that you do this normally is this. You have to start by understanding that you are going to draw a graph, and the graph is going to have time on it at the bottom, just like the gas one in seconds, but up the side is going to be temperature in degrees Celsius. And what you need to do is to have some time when you do not add the zinc. So let's say this is 20 seconds, 40 seconds, 60 seconds, 80 seconds, and so on. Let's say you do not add the zinc until 60 seconds. This is because we need to know that the temperature is constant along here, okay? We need to know because let's say the copper sulfate starts at a slightly higher temperature, okay? So let's say it starts a little bit higher. So I'm going to just draw my graph. I'm going to come down and draw my graph bigger. Oops, not that high. Come on. Right. Whoops, sorry. Okay, so I'm going to draw my graph and it's going to look like this. I'm going to draw, this is going to be my y-axis, this is my x-axis. Sorry about that not being very good. Time in seconds along the bottom and temperature in degrees Celsius up the side. Let's say that I just added the zinc. And let's say that the temperature here is 20 degrees Celsius, okay? Let us say that the room temperature is 25 degrees Celsius. The reason I want to not add the zinc straight away is because the copper sulfate might warm up. Let us say it has been in a cupboard which is a little bit cold. So what I do is for 20 and 40 and 60 and maybe 80 and 100 and 120 seconds, I do not add the zinc. So what I find is that it warms up very slightly. The copper sulfate warms up because it is in a slightly warmer room. Now is it 22 degrees Celsius, okay? And then I add the zinc. And what is important is that you use the stirring rod or the thermometer to stir continuously all the time, okay? This is really, really important. Stir continuously. That is really important. If you do not, the heat will not be transferred properly. So the heat starts to go, the temperature starts to go up. I keep on measuring it every 20 seconds. It slows down. And then eventually it starts to go down. Now, this is really important. So my graph looks like this. So it goes up here a bit, a very bad graph, sorry. And it comes from here down. Ooh, this is a rubbish line. Sorry, I can't draw very well today. And it goes down here like this. Now, what I want to know is what happens in terms of the proper temperature rise. Let's say this here says 60 degrees Celsius. This looks like 38 degrees Celsius. Okay, so this looks like 38 degrees Celsius, but it's not, because this here is the cooling effect. So what I need to do is I need to take a ruler and I put it on this and I draw a straight line like this. And I find where I added zinc here, and I draw straight up and I get a line here. That is the proper change in temperature. From where I added the zinc, the temperature from where I added the zinc, which we said was 22, up to here, which is where the temperature would have got to if it was not cooling down. All the way up here, where it is rising up here, getting hotter, it is also cooling. Okay, so we get rid of the cooling by doing this. So this is the maximum temperature without cooling. That's important, without the cooling. That's a really, really important idea. You need to look at that. Okay? So let's say this goes up to 70 degrees Celsius. Now it's 22 up to 70. So delta T is 48, not 38 degrees Celsius. Now the temperature change, which we called Q, is M times C times delta T. This is the mass of the solution, of the water in the solution. This is the specific heat capacity of water, which you will be given, and this is the change in temperature. So let us say, at the top I said we had, did I say? Yeah, 25 cubic centimeters of copper sulfate. So because the density of water is 1 gram per cubic centimeter, so Q equals 25 for the mass times 4.18, you will be given this, times 48 degrees Celsius. That is Q. Okay, that is how you work it out. If you want to work out delta H, you divide this by the number of moles of zinc. Okay, so that's what you have to do. That's how you do that sort of calculation. That's really, really important that we know how to do that. Okay. So let's look at it again. Whoops, come down, come down. A bit more. Okay. Let's see if we can watch that again. Okay, so we draw a graph and we've got time, horrible handwriting, in seconds, temperature in degrees Celsius up the side. We start at a particular temperature with the copper sulfate, let's say it's 20, but we wait some time before we add the zinc. So we have to wait some seconds to make sure that the temperature of the copper sulfate is constant. So we draw it and we let it go on for some time. If we do that, then we are sure that we know that it is now stable. So I said this was at 22 degrees Celsius. That's really important. The second thing which is really important is that we stir continuously. In other words, when we add the zinc, I stir all the way until I stop measuring. Okay, I keep on stirring all the time. So here's the temperature. It starts to go up. It goes up every 20 seconds. I measure it. I plot it on the graph, and then it starts to go down. And I only stop measuring when it goes down. If I look at this highest point and I read across, on mine, I've said it's 60 degrees Celsius. This is not the temperature that it would have got to if it was not cooling, because heat is lost to the atmosphere. So I take this line here and I extrapolate it. That means run it back. So I extrapolate it back until I get rid of the cooling effect of it, where it's cooling down. And I do that by drawing a straight line through these points back to directly over where I added the zinc. Okay, so this is where I added the zinc at 120 seconds. And my total temperature rise is actually from this temperature up to vertically above it where it meets that line. Now, the amount of energy which is given out will be dealing with this cooling here. We are dealing with the heating and the cooling. So the maximum temperature now, we've said, is instead of 60, let's say it's 70. It doesn't matter what it is. That's what you do. And now the delta T is 48, not 38. Now Q is mc delta T. That's the mass of the water or solution. Not everything, just the water, just the solution, the specific heat of capacity of water which you will be given, and the delta T which you've worked out. To work out the number of moles, the delta H, you have to put it over the number of moles of the zinc in this case, okay? All right. There is something else. Oops. Oh yes. I'm not doing the calculation, but let's say that the calculation comes out as 28.5 kilojoules per mole. I'm making this up, okay? If it gave out heat, in other words, if it got hotter, you have to remember that this will be negative, meaning exothermic. So in other words, there will be maybe one or just a half a mark for saying it's exothermic. In other words, the heat is lost. It's a negative delta H. Okay, you must remember to add the sign. If it gets hotter, it's negative. If it gets colder, it's positive. Okay. So that is so far the first type, simple. The second type, titration, do it very carefully. The third type, measuring temperature, wait for a bit before you add the zinc, stir all the time, measure the maximum temperature it gets to, all very important. Don't forget the sign. Have we got any questions about all of that yet? Is that sort of okay? Horrible? Okay, okay, good. Okay, just remember the practical bits are really, really important. I promise you, they are really important. They make all the difference to how accurate your measurements are. Okay, so let's move on to the last two bits, just two more bits of it. So the next bits are to do with organic and inorganic analysis. And I'm just going to go through the main tests for organic and for inorganic, okay, the main tests, because they don't, although you have to remember many, many, many tests, actually in paper 3, they only cover Very few, because most of them are too difficult to test for in the laboratory. So this one is a good example. Bromine water is normally a yellow-orange color. Don't bother writing this. Do not write this. Kabiro, do not write this. Kabiro, stop writing. Kabiro are going to write. Okay. So bromine water is orangey yellow color. And if there is an alkene or an alkyne, it goes colorless. You have to shake it. But if you add it to an alkane or an alkanol or an alkanoic acid, nothing happens. Very important that nothing happens. So what are the main tests? So let's just go through the main tests for organic chemistry. Okay, these are the ones which keep on coming up. Oops, what is happening there? Don't know. Let's just get rid of that. Ooh, hello. Okay. So the main things that they ask you to do. The first thing is, does it burn? If it is yes, then it means it is an alkane, an alkene, an alkyne, or an alkanol. Is it with a yellow flame, or soot, or smoke? If that is yes, then it is an alkene or an alkyne. If it is not yellow flame, then it is an alkanol or an alkane. Whoops, alkane. Okay, so does it burn? Yes. Does it have a yellow flame? Does it produce soot or smoke? Yes, alkene, alkyne. No, alkanol or alkane. If it does not burn, it is probably an alkanoic acid. Now, most of the time, they are giving you an alkene or an alkyne. The second thing is using bromine water. Now, bromine water is orange-yellow, depending on the concentration. And the question is, does it decolorize? If it's yes, then it is an alkene or an alkyne. If it is no, then it is an alkane or an alkanol or an alkanoic acid. Okay, so we've got burn it and then add bromine water to it. Then what they often do is they add sodium carbonate to it. Sometimes they add bicarbonate, sodium hydrogen carbonate. And the question is, does it fizz? Effervesce? And if the answer is yes, then it's an alkanoic acid. If the answer is no, then it's a hydrocarbon like alkane, alkene, alkyne, or an alkanol. Okay, that's does it fizz with a carbonate? Because acids fizz with carbonates. And the last one is warm with K2Cr2O7 and acid. That's potassium dichromate. Now, potassium dichromate is orange. And the question is, does it go green? And if it's yes, it's normally an alkanol. And if it stays orange, then it's all the other ones. Okay, so those are the main changes. Now they can do it with potassium permanganate, potassium manganate 7 here, which is purple, which goes colorless, but the answer is the same. It's the alkanol, which is oxidized. Okay, so it is oxidized. That's the point about it. All right, so back up. First thing they ask is they probably tell you to get a spatula and pick up just a couple of drops and burn it. Watch the flame very carefully. Is it a yellow flame? Does it leave black? Does it smoke? Does it have a smoky flame? Look up at the flame, look above the flame. If it's yes, then it is unsaturated. So here we can write, if in our inferences, we can say unsaturated, alkene or alkyne, unsaturated. If it doesn't give, if it doesn't burn, then it's an alkanoic acid. But if it does burn, but it burns cleanly, it's probably an alkanol, but it might be an alkane. Alkanols are more common. Then they ask you to add bromine water. Be careful with bromine water because it is very bad for you. Don't smell it. Don't get it on your skin. It's orange or yellow. Does it decolorize? You just add a couple of drops, shake it. If it decolorizes, it's unsaturated. Okay, again, unsaturated. That means there's an alkene or an alkyne. If it doesn't decolorize, if it stays orange, then it's an alkane or an alkanoic acid. They sometimes ask you to add a carbonate. If it fizzes, effervesces, and the carbon dioxide and it gives off a gas, you can test the gas with a lit splint. If the lit splint goes out really fast, it's carbon dioxide. That is from an alkanoic acid. Okay, if it's not, then it's a hydrocarbon or an alkanol. And finally, they might ask you to try to oxidize it. If you try and oxidize it, they will normally ask you to warm it with potassium dichromate in acid. And if it goes green, it has been oxidized, and that tells you it is an alkanol. Inorganic analysis is a bit more complicated, which is why I've got the silly picture here of the person a bit confused. I'm just going to go through some of the most common problems with this, okay? Or the most common tests with their results. So here we go. I'll move up our page. Whoops. Come on. Right. Okay, so let's say we're trying to find the cation first. The cation, some of you will remember I write cation like this, which is how I remember that it is a positive ion. Cation with the T like a plus. Now, normally you take the solution and you have your solution and you add sodium hydroxide to it first. Add it in drops first, then in excess. So just add like literally 1 or 2 drops to start with. Do we get a PPT? Do we get a precipitate? If it's yes, is it colored? If it's colored, that's great, because if it's blue, it's copper. If it's green, it's iron 2. If it's orange, it's iron 3. Those are the most common ones. If it's yes, but it's not coloured, in other words, it's white, then there are many things it could be. There are many, many things it could be. So then you add excess. If it dissolves in excess, then it's ZAP. ZAP is for zinc, aluminium, or lead. ZnAl or Pb. Okay, if it dissolves in excess sodium hydroxide, then it is ZAP. It is zinc or aluminium or lead. Try and remember that. ZAP. You add your sodium hydroxide, it forms a white precipitate, but that dissolves in excess, that's ZAP. If it's no, it doesn't dissolve, then it's probably Mg2+. There are other things it can be, but it's almost always Mg2+. If there is no precipitate, then it might be group 1 or ammonia. Sorry, ammonium. Whoops, sorry. Ammonium. If there's no precipitate, then we warm it and we test for a gas. And if it's this, red litmus goes blue. And that's because its ammonia gas is produced and goes off. That makes it ammonium. Okay, that's ammonium. Now that's the most common of the tests. There is also doing the same with ammonium hydroxide. So if we repeat, so that number 2 is with NH4OH, not NaOH, then it's really looking at Za and P. And Zn2 plus dissolves, and Al3 plus and lead does not. Okay, so if you're using it with ammonium hydroxide, when you get the precipitate, zinc dissolves in excess, but aluminium and lead don't. Okay, that's quite important. That's the way that we tell the difference between ZAP. ZAP is are the amphoteric ones, the ones which form a white precipitate, and then the white precipitate redissolves in sodium hydroxide. Finally, anions. The first one is add acid. If it effervesces, it is CO3 2- or HCO3-. That's it. If it actually effervesces. If it bubbles, it might be something different. But if it effervesces, in other words, bubbles a lot, it is carbon dioxide. Just CO2 extinguishes a lit splint, remember. So try and collect it and just check it. Okay, that's the carbon dioxide. Barium chloride or barium nitrate is added. Do I get a white PPT? If yes, then it is a sulfate, a sulfite, or a carbonate. So then, if it's one of these, I add acid. If I add an acid, then these two will dissolve, and we would be left with that. So if we get a white precipitate, add some acid, and if it doesn't dissolve with the acid, I have sulfate. If I don't have, then it could be a halide. In other words, Cl minus, Br minus, I minus. And these guys all give a precipitate with silver nitrate, yellow, cream, white, I minus, Br minus, Cl minus. The only other thing we have sometimes is up here. They're the most common ones. With this here, with the sodium hydroxide, up here, whoops, sorry. Up here, sometimes they ask you to add aluminium. It's really an anion test. So if they ask you to add sodium hydroxide, then aluminium or zinc, and warm it, and if it gives ammonia, that's red litmus goes blue, then that tells you it was a nitrate. Okay? Okay, that's a lot of chemistry. That is a lot of chemistry. So I'm going to stop recording